Okay, graph definition, right? So it's a collection of a node, also called a vertex. Okay, so we're using vertex more compared with node on graph, but it's the same concept, node, okay? Also the edges, okay? So that's the edges is connecting between each of node. They have terminology called the edges. Notation, right? We have the notation. Graph equal to V and E. V is a set of vertex. E is a set of the edges. Okay, so it means what? How to describe the edges? The pair of the vertex. For example, we have if we talk about the vertex, right? So in this case, the vertex what? Have the A, B, C, D, E, right? So that's the vertex. Okay, so we describe the edge. For example, they're all linked. Okay, so all the vertex being linked together. So the edge, the set of edge will be AB, like AC, AD, right? And AE, and then from B, BC, BD, BE, from C, CD, CE, and then from D and DE. Okay, so that's a linking, that describes the edge. Okay, that's a graph. That's a general definition of the graph. Okay, let's look at some of the type of the graph. Okay, so type of graph. Before we dig into that, just the general concept regarding for data structure. One-to-one, linear, we can solve one problem, right? It's a linear issue. For tree, we can solve one-to-many issue. We already make some examples, right? But many-to-many, the graph can solve way more problem compared with the pure source, the pure two. But unfortunately, this course, we just describe some small portion of a graph. The graph being using very widely, very widely. Okay, so okay, let's dig into some of the type of a graph. First, based on the direction. Okay, based on direction. So for direction, we have the undirected graph. So which means the edge has no direction. Okay, and also directed graph or D graph. Okay, so the edge have the direction. This means from one vertex to another vertex. They define the direction. Same example here. This one is what? Non-direction, right? This don't have any direction. You can go from A to B or B to A. Okay? So from the edge, the set of edge, we just see that, right? A, B, A, C, A, D, A, E, B, C, B, D, B, E, C, D, C, D, E. Okay? So it's based on the order for what? By the combination. Okay? Just based on the number of the vertex, based on combination. Okay? Like this way, once we defined, like this is a graph, we define what? The arrow, right? So it means they define the direction. For example, for here, you cannot go from A to B. It's only apply for B to A because it defines the direction. Okay? So in this case, we define the edge. We need to define the direction, right? For B to A, C to A, E to A, right? And E to A, right? C to B, and D to B, B to E, C to D, and C to E, and so on. Okay, so there'll be less, okay, much less of the unidirectional graph. All right? Okay, so we also introduce the degree, okay, degree of a node or degree of the vertex. For undirected graph, the degree means the number of the edge connect to the vertex. Each edge increase the degree on both connect vertex by 1. For example, this is the undirected graph, right? For degree of vertex B, we just count what? How many edges, right? 1, 2, 3, 4. That's 4, right? So in this case, for all the vertex, they all have the degree of 4. Okay. And for direct, okay, you have a define the direction, right? Direct graph have 2 types, okay, of degree. One's in degree, so it means the number of the edge coming into the node. Also the out degree, so it's number of the edges go out from this vertex. Let's still define the B in this graph. So we have the in degree is coming in, right? From C to B, right? D to B. That's degrees of this in degree of the vertex B is 2. And out degree, it's from B to A and B to E is still 2. Okay? So for direct graph, we have the in degree and the out degree. So here's some of the relationship we can define regarding for degree. In an undirected graph, the sum of the degree of all the node or all the vertex equal to 2 times the number of the edge. So this is easy to understand, right? Okay, so there will be, because it have the, each of the edge have 2 vertex, right? Once you count, in total, will be double, okay, total of the edge. But in the direct graph, okay, in total of the in degree will be equal to the total of the out degree. So the total means each of the vertex, in degree and the out degree summed together, they're equal. Okay, also equal to the number of edge. All right. Okay. Besides the direction, we also can define by what? By the weight. We need to define each of the, because each of the edge have a different weight, right? So we can define the unweighted graph and the weighted graph. Unweighted graph, it means all the edge have the equal, right? Have the equal weight. So it means no weight, just treat them equally. Weighted graph, each of edge have the numerical value, have a different weight. Okay. So for example, on the map, right? On the map, on the different, we can check at each of the location you are planning to go, right? As each of the vertex. Okay, so each of the edge is based on the path you from from A to B, right? But it's from B to C, right? From different location. But things like different, they have a different one. Each of edge have a different distance, right? If you want to evaluate the how long you go from A to B, B to C, you have to define the weight for each of paths. Okay, so it's easy to understand, right? Okay, so same example here is unweighted because nothing labeled for each of edge. Unweighted. And okay, so for this one, if we label that, for example, from B to A, we label as 1, okay, is a cost, but numerical as 1. From B to E, we numerical as 6, right? So different paths have different value. Okay, have different value. This means the weighted graph. Okay. So this also we based on what? Cyclic or uncyclic, right? Cyclic graph is contains at least one circle. Okay, so one circle means the path we can start and end. We can have the circularized, right? Have start and end at the same vertex. Okay, for example, right? We can find the path from A to B to C and back to A. Okay. So the circular, right? If you have the no circle, right? So we call the in-circular graph, right? For example, in this way, right? I only have paths from B to A or C to A. Okay, there's no circle in this kind of graph. And also we have other defined. For example, here we have the connect and connected or disconnected graph. Connected graph, the definition is there is a path between every pair of vertex. Okay, so every pair of vertex, there's a path. Disconnected, some of vertex is not reachable. from others. For example, same example. So it means every pair of the vertex, right? You can find the path in this case. Okay. So it means this is a graph as connected. And this one, some of vertex unreachable, right? What do you mean? B to C is unreachable. Okay. Make sense? Okay. You cannot find the path from B to C. Okay. They define direction here. Only have B to A and C to A. Okay. Complete graph. Complete graph is every pair of the distinct vertical is connected by a edge. So every pair, okay, pair of vertex A, B, and C, they have the unique path being connected, okay, by one edge, okay. So, for example, if you don't have A to C connection here, it's not complete, even though you can find a path from A to C. Okay, for example, this is edge not exist, right? This means it's not complete. Okay, even though you can find a path from A to C. This is called the connected path, connected graph, but not complete graph. What about this one? Is it complete or not? Not complete, right? Because why? Because from B to D, there's not directly edge to connect with, right? And A to C, there's not directly path to connect with, okay? But once we link them together, it's it becomes complete, okay? Complete graph. Right. And then they call the loop graph, okay? Loop graph. What's a loop graph mean? So it contains at least one self loop. Okay, you start from U and then without other vertex, you end from U. The self loop. So edge connecting the vertex to itself. Okay, so that can be direct or indirect. So for example, in this case, this is a loop, right? It's a loop graph, right? Because they have the self loop from B to B. Okay. Oops. So if this is a undirect, right? If the direct, so we can define the direction, right? From B to B, whatever. Okay. All right. Simple graph. Simple graph, which usually is defined the undirected graph, so it means has no loop. One condition has no loop. Second condition has no multiple edges. What does it mean here? First, no loop is no edge connect a vertex to self. For example, in this one, how can we make them as a simple graph? We just remove the loop, right? Remove loop, it can become the simple graph, right? Okay, what about this one? So from B to C, they have a multiple paths, right? So it means multiple edge. So if we want to convert to the simple graph, we need to have to remove the extra edge from B to C. If you remove that, this becomes the simple graph. Okay. Sparse and dense graph. What's a sparse? Sparse graph. So its number of edges is much less than the maximum possible. Okay. Dense, number of edges close to the maximum possible. What do I mean? For example, this graph. If we can count, okay, for this graph, right? If you want to calculate the maximum number of edges, okay, for example, we have a 4 node, right? 1, 2, 3, 4 vertex. What maximum edges you can have? If you want to build a direct graph, what the maximum edges? They all fill in like this way, right? A to B, B to C, A to B, B to A, right? Bidirectional, right? B to C, C to B, right? And A to D, D to A, A to C, C to A, right? All connected, right? So for A, how many paths? How many edges can I have it? What? Six. Okay. 1, 2, 3, and times 2, right? For B, how many? Same thing, right? And C to B, all same thing, right? So it means how to calculate it in this way, though. So 6 is equal to what? V minus 1, right? Number of the edges, because this itself to remove. Okay? We don't count self. So it's V minus 1 times what? Times V. Maybe something wrong here. Oh, something wrong, sorry. We just count 1 for direct, undirect. Okay, sorry. Okay, here. For undirect, we count 1, 2, 3, right? For each of 1, 2, 3. And for B is 1, 2, 3. So for A is 1, 2, 3. Okay, so count 3 times. For B, it's count again, 1, 2, 3, right? 3 times. So it should be V times V minus 1. Make sense? Because they count what? Count twice. Okay? Maximum of edges, right? So if you have a direct, right? We have a direct. We just define the one direction. Just define one direction. The maximum number we just divide by 2. Make sense? Okay? From A it should be 3, not 6. Okay? Because you count B, it's 3 as well. Okay? Yeah. Okay. Yeah, so some mistake here. Okay? I recalculate. So here, the maximum age is for unidirectional is V times V minus 1. For direct graph, it's V times V minus 1 divided by 2. Okay, so maximum of the age. Okay, so based on definition, right, a spherical graph, which means much less than maximum possible number of age. So it means E much less than what? V squared. Why we define V squared? If we spread them together, right, we have a V squared minus V. Okay? Here I have V squared minus V divided by 2. Okay? For squared graph, we take the V squared part. That's the definition, okay? We take a V squared part. Okay? Much less than what? Much less than V squared. So the big O will be what? We focus on what? Focus on the much less, but between the what? Between the V and V squared, right? So the big O of this case will be equivalent to the big O of V. So for example, in this case, okay, in this case, we can call the spiral graph because the path is close to the big O of V. It's a linear relationship. And for dense graph, it's close to the V square. Okay, so the number of edges close to the big O of V square. For example, in this graph, we call the dense graph. Okay, so all the paths being linked together. Okay, so for dense graph, also we call the complete graph. Okay, by definition. Okay, so let's go through something that the application being used by the graph. First is navigation, map. We've been using a lot, right? Google Map. Before I have GPS, right? I have a device for GPS. Google Map and the Azure Map, all the map technologies we're using by the graph. we can define the node or vertex by the what? By different location, set of location. And the edges is the road, right? Routes or flights or ferry, okay, whatever. We can define each of weights, right? Based on distance, right? Or based on the time being cost, right? Based on the traffic cost, okay? We can define the different weights. The algorithm being used, right? And we have the what? Desk tree, A star, Florida wall shell. So that's something algorithm being used for the path funding. We'll be learning this too, okay? Destra and Florida wall shell, these two, in next lectures. So it's been used in Google Map or GPS system, okay? It's also being used in internet and the web server, internet. We can have define the vertex or node, each of the web page as what? As a node. Edges, each of the hyperlink on the edges, right? Using for what? Like the page ranking, right? Ranked pages. For example, for Google page rank for algorithm, right? So doing a search, have a different rank, pump up the different kind of ranking on the result. Social network on Facebook, right? For example, Facebook or X, or before Twitter, been using that a lot, right? For define the node or vertex as each of the people, right? We can define the different user, right? Edges by the connection, right? So either they follow this person, it's one direction, right? Just have a directional graph, or the friend. If a friend, it's a non-direction, right? So both a friend, but you just follow one direction for the different people. So it's useful for suggestion, right? Community detection and influencer ranking. Originally, like they usually give you the recommendation of friend. It's based on what? Based on your friend group and their friend group. Okay. If you have one person have a friend connection, they'll be detect. Okay. If the other person you may know about, right? Because you have the same friend. All right. They're using graph to build this connection. Okay. Computer network. Okay, so we can define the vertex or node at each of computer or each of routers at home, right? And then on the edges, build each of connection. Okay, so for example, we're using network routing, packet delivery, load balancing, right? Okay. Biology, okay, bioinformatics. We can define the vertex as a genetic genes, right? Proteins, cells. So what target you want to do research, and build the edges like interaction. Okay, different genes what being interacted, different proteins, by how to link up between the gene and the protein, right? And how the cells being built up by different protein. Okay, using what? Metabological pathway or protein-to-protein interaction network. Been using a lot of research by graph. Recommendation system. Okay, recommendation system. For recommendation system, we can define what? Vertex as the user. All right, and edges based on what the history of your purchase, history of your search. Okay, and like your view, what you're being liked. This can be in the what? Build at the edges as edge. Based on this information, they can give you a recommendation. Okay, using what? Netflix, also the Facebook, right? Been using a lot. Amazon, mainly in the e-commerce website, they're using a lot. Okay, Shopify, right? Game development. Gaming using the what? Using graph a lot. The highly used graph. Okay, it's very complicated, including the other visualization, right? They're using a graph, the map. Okay, so if you play some game, they have a map. Okay, if you go one direction to another direction, you have a logic, right? Algorithm to find the right path, right? So it's all being using on the graphs. For example, using the game map, path funding, the graph color for tile-based map. Okay, for tile-based map, you can define the graph and define each of color. Okay, different value for different type of color. Define the graph coloring. Okay, they have been using on the graph. Also the machine learning. Okay, the machine learning AI using the graph a lot. Heavily using graph a lot as well. Okay, that's good though. So we cover a lot of graph. Sounds very powerful. How to implement on the code? Okay, how to implement on the code? Any thought?
Just set up a node with
Set
receiving
node.
and sending.
Yeah. Okay. Just simplest way. Simplest way. I want to build a graph. I want to build a map. How to do that? Right. 2D array. Right. Simplest 2D array. We can build a graph. Right. Yeah. Using 2D array. Okay. 2-dimensional array. We define the graph at that dimensional array. Each of the vertex, number of vertex. Okay. And then this for what? To build what? The edge, right? So either you have the edge between each of the vertex or not. Or you can define the weight if it's a weighted graph, right? Define a different weight. So they call the adjacency matrix, right? Am I pronounced right? Adjacency, okay. Adjacency matrix, okay. It's just a terminology, okay. But actually a very simple concept. And then they put a very fancy terminology and make a new research and publish a paper. That's how that works, so research. For example, this graph, this is a weighted graph, right? How can I build the 2D? How can I use the 2D array to represent this graph? We build a what? 5 times 5 2D array, okay? And how that works here, how being laid out. Okay. We can list each of the vertex, right? From A to E, and then from A to E. And then we want to build their what? Relationship, right? Okay. So we need to define whether they have a connect or not. So define the age and the corresponding the weight. So for example, from A to A, they don't have the loop. So that's why they don't have the tags, right? Don't have age from A to A. Define the 0, it means what? Once you see the 0, it means it's no relation between A and A to A. There's no age between them, right? So from A to B, we have it, right? And then also weight is what? Weight is 6. So define 6. Okay. And from A to C, anything regarding for A to C? Nothing. Not directly. Okay. For A to C is 0. And A to D, you have it, right? A to D, you have the relationship, right? Here you have 8, the weight of 8 equals 1. And then we put a 1 here. And then A to E, it's now age between the A and E, right? So A to E is 0. So now we can build the what? Build a graph. Okay. And build, to use this number to represent each of the vertex relationship. Okay. Also ages. So from B, right? From B, same thing, right? B to A and B to A, they have it, right? It's 6, right? And then B to C, they have it, right? B to C have 5. B to B, they have nothing, right? B to B has nothing, 0. B to D and B to E, they are both have it, so it's 2 and 2. Make sense? Same principle from C, right? C we can build what? C to A is nothing, from 0. C to B, we have it, 5, right? C to C from nothing, okay? And C to D, is not direct relationship, right? 0. And C to E is 5. D is the same thing, right? D to A, we have the path, right? And weight is 1. D to B is 2, right? D to C, 0. Okay. D to D is 0. D to E is 1. And then we focus on E. E to A is now relation 0. E to B is 2, right? E to C is 5. E to D is 1. E to E is 0. Okay? That's now we can use 2D to describe this graph and use the relationship, right? Okay, have you guys noticed there's any for this 2D, right? For this matrix, is there any character? Yeah, it's the same. From here, same. Okay. So from this line, from diagnostic line, you can see the symmetry, right? So this is a match, right? So symmetry along the adjacency matrix, diagonal, right? That's our matrix. So this is play for what type of graph? Only for on-directional graph. If there's no direction defined, we can see this matrix is symmetry by the diagnostic line. Okay. Let's see how we can apply the code. Okay. So on the code, we define what 2D is by what? Not by ABCD, by what? By the index. We need to assign each of the vertex as the index. That's the first thing we need to do. Okay, ABC represent index from 0 to 4. Okay. So here, that's a code. We have the number of vertex equal to 5, right? And then define the 2D array, graph 2D array. Initialize as all 0. And then we will define the web value. Okay. From here, 0 to 0. 0 to 0 is 0. We don't need to define, right? 0 to 1 is 6, right? 0 to, from here. 0 to 1 is 6. And 0 to 3, 0 to 2 is 0, right? 0 to 3 is 1. 0 to, and then 0 to 4 is 0. Nothing, we don't need to define. And then jump to 1, right? 1 to 0 is 6, right? 1 to 0 is 6. And 1 to 2 is 5. 1 to 1 is 0. We don't need to define. And 1 to 3 is 2. 1 to 4 is 2. Okay? So this will be, we'll continue to define, set up the weight in this 2D array. Okay? So we can build this matrix for this graph. Okay. For directional graph, we can only set what? For directional graph, we can only set graph U and V equal to 1. No, it's not right. Let's skip this part. So we know it's not matrix, right? We know it's not matrix for directional graph. So for directional graph, we only allow to say, okay, U is start vertex, V is end vertex. Okay, so they have a direction. You only allow to assign, for example, you from A to B, right? You only allow to assign A to B. There's now B to A. Okay, so that's what I mean. Sorry, so this is not matrix, that's why. So weighted graph, for unweighted graph, will be replace 1 with actually weight. Just unweighted. Okay, there's a pros and cons regarding for this defined for using 2D array to approach. First, this is good for the dense graph. Why is it good for dense graph? We just know a dense graph because dense graph have the many paths, right? Many edges. So this can fully represent the relationship between each of the vertex. Okay, so it's easy to check whether the edge exists or not. So how to check? We just know the each of the index. We can verify that if the 0, it means no edge. If the not 0, it means have the edge, right? But they also have the cons. This means waste of space, right? We're using how big space? Using v times 2, v two dimension, right? V times v, right? So it's a waste of space. Okay, so besides the 2D array, what other things we can use to describe the graph? to implement a graph. Besides 2D, we have been learning a lot of data structures. Nodes class, we can use that. Okay, we can use this stuff, right? We can use the list. Okay, we can use the list. We have a vector, and inside the vector, we represent each of the edges. Okay, using the list or the sorted map. And each of the vertex stores a list of the neighbor. Okay, each of to store the list of this vertex neighbor. We call the adjacency list. So let's describe this. Okay, same graph. First, we need to define the vertex. From vertex, we know it's from the A, B, C, D, E, right? And then we know this part, right? We know this part, okay? Or this part. And then we want to each vertex adjacency list. So we need to find the other neighbor. For example, the first one, A, what's the neighbor? We have the A and B have a connection, right? And A and D have connection. Okay, so it means for A, they have a B and D. For B, they have a weight 6, right? For D, they have weight 1. Okay, so this part is here to define. Will be list of the neighbors. For B, we can find they have the A, they have D, have E, and have C. Okay, so in this case, we can make this list, right? And add the corresponding weight. 6 from B to A, they have weight 6. B to D, they have weight 2. And B to E, they have weight of the 2 as well. B to C, they have weight of 5. For C, they have a B and E, right? And the all weight is 5. For D, they have the connection with A, B, and E. A, B, E. For their weight is 1 and 2 and 1. For last one, for E, they have the connection within D, B, and C. Their weight is 1 and 2 and 5. Okay? Now we build the relationship using list. Okay? Using list, each of the list. Okay? Inside the list, they build a sublist. Okay? To connect each of their neighbor and the corresponding weight. Okay, let's see how to implement on the code. So we need to convert into A, B, C, D, E into a again, similar with the index, okay? We label as 0, 1, 2, 3, 4, right? And then we become like that, okay? So 0, 1, 2, 3, 4, and then we change the corresponding, the vertex as a number, numerical, okay? So it's easy to deal with, right, on the graph itself. Okay, so for example, A, B, right, B change to 1, right, D change to 3, and so on. Okay? Okay, from here, let's implement by the code. This is the code here. We create the list of we have vector, right? And then inside, we have another vector. We have a vector of this, of vertex. This is this vector. And then for each of the vertex, we have this vector. Okay, that's what this vector is. And for inside of each of these neighbors, they need to define the pair, right? Both are integer. This is a neighbor, indication of a neighbor, and then this is a weight. Okay, this is a weight. This is an indication of a neighbor, and this is a weight. Okay, define this graph. Okay, so and then we just using the to graph 0. Graph 0 is this vertex, right? Graph 0 and push back into their neighbors. Push back to 1, 2, 1, 6, 1, 6, and then 3, 1, and then this is done, right? And then we push back into which one? What is vertex number 1, right? Graph 1 and push back to 0, 6, 3 to 2, 4, 2, 2, 5, and then and so on. Okay, so will be graph index 2, push over this and this until the end, right? Push over 4 on the graph 4, right? Vertex 4, push back into the 3, 1, 1, 2, and 2, 5. That's how that works. This also can using what? Unsorted map. Map is have the key pairs, right? They define the, you have to define the key. The key is what? The number of the vertex, okay, based on vertex. And then you can customize regarding for the value is, right? Okay? So if we have the weighted, right, graph, if unweighted, we don't need to define this value. We just need to define the what? Only one integer, okay? Just have the path. Once you have it, and you between this between the A and the B have the edge, right? Okay. The good part is good for the spiral graph, okay, in this case, because it's now probably not many connection, okay? So we're just using this the list to build a connection. We don't need the 2D, right? In 2D, we have waste a lot of space. And then less space taking, right? Cons, if you want to check the edge exists or not, it's taking a little bit longer time to process, because we need to verify it. For example, we want to connect between this is B to D, right? We have to find the B, right, from here and run inside the list. Okay, you have to the complexity can turn to what? Big O of degree. Big O of degree. How many paths connected into the D, right? Okay, so and also it's complex to implement. So this is easy to make a mistake. Okay, and sometimes hard to debug. You don't know what's going on, where mistake you made, right? Once you initialize the graph, is wrong. Okay, the result may be wrong. But 2D is relatively easier to define. Okay. Okay, good though. There's a third option is a edge list. What's the edge list? Similar with this list, but we don't need this. We don't need the vertex. Define the vertex. Okay. How we can do? We just list all the edges in the path. Okay. Each of edges store as a pair or triple if there's a weight. Okay. So for example, if unweighted, we just use a pair. Okay. So from the star, from the what? From the start vertex until end vertex. Weighted, we add one more, right? Star vertex, end vertex, and their weight. U is star vertex. Okay, V is end vertex. Okay, so this we're using the edge list to define the graph. So this sounds a little bit chaos, right? If we just have a lot of the big graph, you don't know what's going on, right? Okay, same thing. Same example. If we're using the edge list, what we define here? Start vertex A and the vertex B, for example, this one, and define the weight 6, right? And then A and D equal to 1, B, A, 6, B, D equal to 2, right? B, C equal to 5, and so on. Okay? So that's all the list we defined. If we convert A, B, C, D, E into the number, numerical number, this is what we get, right? 0, 1, 6, 0, 3, 1, 1, 0, 6, 1, 3, 2, 1, 2, 5, and so on. Okay? Okay, let's apply on the code. That's the code. Pretty straightforward. Okay? We define top, right? Integer, integer, integer. And then we just push back. Okay? Push back all the value. Right? The promise is simple to implement, right? Very simple to implement. And compact for sparse graph. Okay? For sparse graph, it's a good, you use this, it's okay. It's not many paths to be built, right? And a smaller graph, you can easier to implement. Great for the edge-based algorithm, okay? So this is define each of the edges. So for edge-based algorithm, they can use to implement. There's no wasting of space. Okay, there's no space wasting. They just build a relationship between the two vertices have the relationship. Cons, it's not ideal for the dense graph. Okay, if you have a lot of the paths, so you don't know what's going on, right? Give you this stuff. Okay, you have to think, okay, how to link them together, right? and less structures. So it means very hard to doing the insert, delayed, also hard to search. Okay, slow for search as well. Okay, so there's a 3-way for implement a graph. Okay, so it's a very common 3-way to implement a graph. All right, okay, good though. Next lecture we discuss about some of the algorithm, right? Path finding algorithm stuff. All right.